Hello again, method students. In this video, we're going to start looking at the normal distribution, which is a very sort of special type of probability density function. In the last video, we talked about how we can use functions to represent probability distributions. The normal distribution is a specific type of probability density function, and it's characterized by its bell-curved symmetric shape. You often hear these functions talked about as being a bell curve. And the idea with these functions is that the peak of the bell, the highest point on the curve, occurs at the mean. And that's because these distributions are symmetric. The standard normal distribution, when we talk about the standard normal distribution, we often use the letter Z to represent the standard normal distribution. That's a symmetric bell curve that's centered at x equals 0, and it models a variable that has a mean of 0 and a standard deviation of 1. Remember that standard deviation gives us an idea of how spread out a distribution is. And so, yeah, this is really important here that we're talking about a mean of 0, so mu equals 0, and a standard deviation, sigma, of 1. That's the standard normal distribution. And this is the rule for the function of the standard normal distribution, and this is a graph of it. So you can see from the graph, we've definitely got this sort of bell shape to it. The highest point on the graph occurs where the mean is, and that's at x equals 0. And the rule, it looks a little bit messy, but this is just a rule, an exponential function, or e to the power of negative a half x squared. So it's sort of a composite function, and it's got lots of bits to it. You can see it there for yourself, but this is the rule. This is just a function that produces this bell curve. Now, because the function I guess approaches 0 as we decrease the values of x and also increase the values of x at the other end, it still satisfies what we were talking about in the last section, that the area under the curve, the entire area under this curve, would equal 1, okay? Because as we get closer to negative infinity and positive infinity, we're really not getting any more area under the curve. So even though this graph doesn't actually quite ever hit the x-axis, the enclosed area between the function and the x-axis is 1. And we're also going to look at lots of cases where you have variables where obviously the mean is not always going to be 0 and the standard deviation is not always going to be 1. And so in more general terms, the rule for the normal distribution with any mean and any standard deviation, where we just use those symbols in general terms, is given by f of x equals 1 over the standard deviation times the square root of 2 pi times e to the power of negative a half times x minus the mean divided by the standard deviation, all to the power of 2. Right, it's a pretty messy looking formula. You're not going to be expected to memorize it, but if you know the mean and you know the standard deviation, you can write the function for a normal distribution. One of the other nice things is that these normal distributions are so common and so important that actually the calculator has this function built into it. So most of the time when you're doing calculations, you won't need to come up with this function. You can use calculator commands to actually answer questions much more quickly, but we'll get to that in a couple of videos' time. So, for example, here's a graph of a normal distribution where the mean is 30, because you can see that's what corresponds with the peak of the graph, and the standard deviation is 5. Okay, so you can see that it's relatively spread out there, compared to the previous graph where the standard deviation was only 1, and so the numbers along the x-axis are not as spread out. All right, let's have a look at a couple of examples where we start to kind of explore a bit more that sense of what happens as we change the mean and the variance, or the standard deviation. Remember that the variance is just the standard deviation squared, so they're both representing a similar idea. Okay, so the mean controls where the center of the curve is going to be, and the standard deviation controls the height of the curve and also the width of the curve. So essentially, if the standard deviation is bigger, it's going to make the curve a bit flatter and more spread out. If the standard deviation is quite small, the curve kind of gets a bit narrower and taller. Remembering that the area under the curve has to have a total of 1. Okay, so example 1, for the probability density function that is normally distributed, and it's important that the question actually says that it's normally distributed. You shouldn't just assume that anything has a normal distribution unless you're told. With a mean of 25 and a standard deviation of 3, so we've got mu equals 25, sigma equals 3, write down the rule for the function. So this is just really going back to this formula and putting in a mean of 25 and a standard deviation of 3. So the rule is going to be y equals, now it's 1 over, and I'm just referring back to it here. Like I said, you're not going to have to memorize this. 1 over the standard deviation times the square root of 2 pi times e to the power of negative a half times x minus the mean, so x minus 25, divided by the standard deviation, all to the power of 2. I'm probably could have written that a bit bigger for you, but I hope you can just see clearly enough what that rule is. And let's just sketch the graph of the function. Now, obviously, we could type this into our calculator, but we hopefully already, from the couple of pictures on the previous page, are starting to recognize what these distributions are going to look like. And you can actually sketch the normal distribution by sketching a bell curve. It needs to have a mean of 25, all right? Which means 25 on the x-axis needs to line up with the peak of the graph. And with a standard deviation of 3, what you typically do with these, and again, this is sort of leading into a future section, is you typically mark sort of 3 standard deviations above the mean. And so that would be 28, 31, and 34, and then 3 standard deviations below the mean. I'm just trying to do this as equally as possible without having a proper scale to work with. And so each of these markings on my x-axis is representing 1 standard deviation. Okay. And so that's a rough sketch of the function for this particular normal distribution. Use a calculator to show that the area between the function and the x-axis is equal to 1. Okay, so what we'd be trying to do there is to show that the entire area under this curve is going to equal 1. And the way we can do that is actually to use terminals of negative infinity and positive infinity, and this rule here. So we're going to put in our function that we wrote down in part A of the question. And integrate that with respect to x, and we should hopefully be able to show that that gives us a result of 1. All right, and we do actually get, with a bit of thinking from the calculator, a result of 1. Okay, so that's just one of the conditions that we need to occur in order to have a probability density function. So that's just showing that this particular normal distribution, like any other normal distribution, does indeed satisfy the requirements for being a probability density function. Okay, second example here. This one's actually drawn 2 different normal distributions on the same axis, and it's just asking us to pick the one that has the higher mean and which one has the higher standard deviation. So remember that the mean is dictating where the peak of the curve will be. So this one here has got the peak of the curve at about 5 on the x-axis, whereas this other one's maybe only at about 2. So this graph here has got the higher mean. The standard deviation, remember that the larger the standard deviation, the more spread out the distribution is going to be. So the flatter, wider one is going to be the one that has the higher standard deviation. Okay, so I hope those examples are starting to give you a sense of what the normal distributions are all about. In the next exercise, we go into more detail at looking at variables where we're actually marking these values on and identifying sort of probabilities and percentages underneath these curves. But for now, it's just about getting familiar with the normal distribution curves and how the mean and the standard deviation actually affect what they look like. All right, we'll see you in the next video.